Okay, here's an example problem on channel capacity. And we're talking about Shannon capacity here. And so the first thing I'm going to do is just write down the Shannon equation. And it says that the maximum bit rate is equal to bandwidth times the log base 2 of 1 plus the SNR, where SNR is given as a ratio. And so let's see what we're given here. We're given the bandwidth. So the bandwidth is 30 megahertz, or 30 times 10 to the 6th hertz. We're given a theoretical Shannon capacity of 200 megabits per second. That's our RB value. Megabits per second, or 200 times 10 to the 6th bits per second. And it asks us to solve for the SNR. And so I have to solve this Shannon equation for the signal to noise ratio. Well, the first thing I'm going to do is I'm going to say that the bit rate divided by the bandwidth is equal to the log base 2 of 1 plus SNR. And then I'm going to take both sides of the equation, I'm going to raise 2 to that power. So I get 2 to the RB over bandwidth is equal to 1 plus SNR. Okay, raising 2 to the log 2 power gets rid of they cancel each other out. And so now I can solve for the SNR here. And so the SNR, if I subtract 1 from each side of the equation, SNR is negative 1 plus 2 raised to the ratio of the bit rate to the bandwidth. And this is negative 1 plus 2 raised to the, you know what I can do? I can, if I'm dividing the bit rate and the bandwidth, the 10 to the 6th just cancel out. And so I'm going to just put a 200 over 30 here. And this is negative 1 plus 2 to the 23rds, or let's just plug it into the calculator this way. 2 raised to the, and I'm going to put it in parentheses, 200 divided by 30, right parenthesis, equals, this gives me a 101, and then I subtract a 1. Let's just plug that equation into the calculator. And I got a 101.6 for the 2 to the 230th, and then subtract 1 from that. It's 100.6. I'm just going to say 100. And this is a ratio. Okay. So that's the signal to noise ratio as a ratio. The next part asks for the signal to noise ratio in dB units, and S and R in dB is equal to 10 log 10 of SNR as a ratio, and that's 10 log 10 of 100. The log 10 of 100 is 2, so this is 20 decibels. And that's one of our standard values. We know that 10 as a ratio is 10 dB, 100 is 20 dB, 1000 is 30 dB, and so on. Okay, so next it says, given this SNR value, what's the maximum noise power when the signal power is 10 milliwatts? Okay, so SNR, we can write the signal to noise ratio equation either as a ratio or as in decibels. And I guess I'll write it as a ratio first. Signal to noise ratio is the power of the signal divided by the power of the noise. And it's asking me what is the noise power. And so I can solve this for the noise power. And this is equal to the signal power over the SNR. And this is 10 milliwatts divided by 100 as a ratio. And this is 0.1. 10 100ths is 0.1 milliwatts. Okay, so That's how you can solve this equation using the signal-to-noise ratio as a ratio. If we want to do it in decibel units, we say that the SNR in dB is the power of the signal in dBm minus the power of the noise in dBm. And 10 milliwatts, if we convert that into dBm, it's 10 dBm. 10 is 10 on the decibel scale. And so we end up with, if we want to solve for the noise power, we can solve this equation for noise power, and I get P noise in dBm is power of the signal in dBm minus the SNR in dB. And my signal was 10 dBm minus SNR in decibels was 20, and so I get minus 10 dBm as my noise power, and minus 10 dBm is in fact equal to 0.1 milliwatt if you double check that. Okay, so you can solve it either in decibel units or in linear units. It's easier in linear units because you're already given the signal power in linear units, and you already have the signal-to-noise ratio as a ratio. So, hope that helps on this one. Thanks for listening.